Welcome, everyone. My name's Mark, and this is TeachMePCB. I'm creator of TeachMePCB. You know that because they're stickers, and co-facilitator of this year's course, where we are designing macro pads, little keyboards that you can program to do your bidding, essentially. And you might have noticed something different, and it's a change just from today. You know what it is? Can you tell? We're getting new lighting. So I'm still tweaking it. I just barely got it done before office hours kicked off. But yeah, there's new lighting. It's got like a 97 color rendering index. And I don't know. I'm excited. We'll see how it goes. So a couple of things happened today before I go back. And I guess since nobody's here, I'll play around with my design a little. But we did a hack chat on hackaday.com. That was a lot of fun. I did that with my buddy Greg Zeraldo. And if you read it, if you go back and read the transcript, you'll notice a couple of things. Either I'm his hype man or I'm his stalker and I'm stealing everything that he loves. And I keep it intentionally ambiguous like that for a reason, because it's funny. But if you go back and instead of reading it as me being a hype man, as somebody who's going in there and just stealing things, like I talk about you should try the Greg Zeraldo sandwich. You could read that as though I'm just stealing his lunch every day. It's it's a lot of fun. So I hope you guys enjoyed that. If you didn't get a chance, it was okay. We shared some interesting things. But if you did miss it, it's okay. You're probably not going to be dealing with heavy copper anytime soon. So just know that it's there. And if some point down the road, in a couple of years, you have a need for heavy copper, just go reference it then. Other than that, it wasn't the best presentation of the material in the hack chat. It's a lot easier to do in a video presentation. And we've got those too for this very same subject matter. Other things that are going on this week, we've got your schematic symbol editing. Jesse shared all of his libraries, so you can jump right in and steal his stuff if you've fallen behind. So it's a great time to get back and get started again if you haven't already. So anyhow, with that, since nobody's here with me, by the way, join me. But since nobody's here with me now, we can go ahead and get started going back with the layout that I was doing a couple office hours ago. Oh, looks like I've got somebody joining me. It's my friend Elliott. So he's connecting now. While he's doing that, I'll bring Dip Trace up and get the files ready. Hopefully. It's never the easy way, right? There we go. All right. And Elliott, my friend, there you are. How are you?
What are you doing?
Good, man. How are you?
Great.
Before I jump into really exciting stuff, which is, PCB design, what brings you by this evening?
PCB design.
I love it, man. So how's life?
Oh, that's good. It's good. If we get bored later, I can show you what I've accomplished on that challenge that I'm working on.
I'm bored now. Let's do it.
All right.
Should we tell people what you're doing?
Sure. Yeah. Go for it.
All right. So IPC is a organization that controls printed circuit board standards across the industry. They bring groups of people together and they figure out what the best way to move forward as an industry, so that we can all communicate. The reason that we have standards to begin with is so that different companies can collaborate, all kind of marching along the same direction. Anyways, this year they're doing a competition for IPC Apex, which will be in January. And the companies I represent have a small part in that. We're going to, well, I don't know if I'm allowed to tell yet, so I'm not going to tell you what we're going to do. But one of the things that they have is a preliminary competition before you get to the final rounds. And I've encouraged a course participant named Elliott of Elliott Makes to go ahead and give it a shot. see what you get out of it. So, Elliott, is it true that you didn't really do PCB design before this course?
I've made a handful of through-hole boards and had them
Okay.
manufactured for little projects, but that is
But
it.
okay, so pretty much though, I guess where I'm going with this is your first foray into PCB design, standards based and all that, right?
Yeah, in a serious way, definitely. Before now,
Okay.
it's been Arduinos and breadboards and making connections, but no
So
science.
10 years from now, if somebody's looking back on this video and says, "Oh my God, why did he do that?" Elliott's just getting started, and I guarantee you he's doing better than most would at this point in life. So, hey man, share away.
All right, I think you got my screen there.
I do. Let me add it to our stream and then I'll minimize us.
Cool. So this is they actually dumped a whole bunch of information on me, but the gist of the thing is we've got a schematic, we've got a bomb, and we've got some requirements, and we've got to lay out a board according to these. And yeah, so from the way I'm looking at this is step one, reproduce the schematic in some software we can work with it. This is just a PDF. It doesn't page through properly. But the circuit is FPGA, some flash memory, a couple motor driver chips, a couple buttons, a couple ADCs, and some connectors. So the pages don't page properly, but you can get an idea from that top level schematic. So this kind of just you got to dive in all the concepts we haven't gotten to yet in the class, and then some of them we have. But this is a hierarchical, however you pronounce that, diagram, and then with some of these are repeated. And I think this one was made in Altium, but I'm using KiCad, so it's been a bit of uh, a challenge, I guess. First time I've used that software anyway, so kind of figuring things out. But you've got all the examples of so we've got you notice there's no connections between these. They're all basically net names, and every connection just joins a net, and then somewhere else hopefully is the corresponding one. And also there's some let's see, there's what, two grounds, a chassis ground, and like 3 or 4 different voltages. Bunch of connectors here. I actually have no idea well, not no idea. I can tell the purpose of this is to be some kind of motor driver, but I think it's a bit of a imaginary circuit, and there's some really interesting part about that. So anyways, what I've been doing in my spare time is trying to reproduce this. So I've come up with something, and I actually did my best to mimic what was there. Partially because I don't know what the best way to draw is, and additionally, it's probably, let's see, in order to minimize errors, I'm trying to basically duplicate what I see so that I can check it back and forth. I've made many errors so far, but yeah, same idea. I'm laying things out. I had to create all these symbols. So this symbol here is a 5-part symbol. So I'd be happy to try to help. I'm not a real expert, but I've had recent experience. So if anyone has questions on Discord, I can certainly help. But in this example, actually, I lied. It's 4, but this is the FPGA. It's got 100 pins. You can see it's broken up into A, B, C, and D. So just kind of reproducing what I see, but had to figure out how to make that work. There's a couple special checkboxes. If you don't know about them, you will be disappointed. And yeah, so in general, there's really 1 or 2 tricky requirements. So if we get back to that PDF, there's one that really stood out to me that we'll see in a second. So Ooh, that's stuck to my mouse. That's bad. Uh, so there's a couple things I think we I would appreciate talking about later, and I'm sure we will get to later in the course. But even the concept of impedance is a little foreign to me.
Oh, let's
Um,
definitely talk about that then, because
so
you
I
will
think
need that skill here.
that would be a great topic to go over. It's easy enough to put numbers into calculators, but I need that like layman's understanding and grasp on like not so much what it is, but what factors influence it and why it's measured in ohms.
Okay.
Anyways, so yeah, there's a couple differential pairs in here where that is important, as well as this. This note is actually quite interesting. So there's 140 volts on this board, and in the bill of materials, as well as on this, the sorry, I keep picking up the sheet and it follows my mouse around. This is a, a motor driver, but it's kind of 3D printer sized. Um, and they've got 140 volts going into it, which is absolutely not rated for. So the challenge here is how to have isolation or something like it on this package. And this is a very small chip. So the leads themselves are close enough together that they don't um, they don't really meet the requirement in the first place, traces or otherwise. So yeah, some interesting stuff. Maybe not the most realistic project, but it's here.
Well, yeah, you tend not to see too many FPGA based motor drivers for some reason.
Yeah, so this was interesting. I don't have
Yeah.
3D models of everything, but it's got a almost all of these parts are obsolete. This is an obsolete FPGA. The memory is from like 2002. Um, and it's got like one of those 1602 LCD screens on it.
Oh
And
wow.
doesn't really seem like it fits well with a 140 volt something or other. It's got a couple buttons. Like it just doesn't feel like a realistic product. But oh, you can see here I have some DRC violations.
Yeah, that's
Uh,
going to be your high voltage,
but
right?
this
Yeah.
is the chip. This is I don't know 5. Well, we could measure with the handy tool and see. Actually, I don't have the silk screen turned on. Anyways, it's not a very big chip. I think these are a quarter of a millimeter in height here. So I haven't solved all the problems. What I'm really trying to do is, and I just achieved this a little while ago, is get everything in the space and connect all the dots. So
Okay.
I'm certain I'm going to rip this up 1 or 2 or 3 more times and kind of do a better. Yeah, so far, actually, we can hit this button here.
Well,
I
let's not
actually have,
unroute anything yet because I already saw a couple things I'd like to point out. Oh, you're doing
oh,
3D. Okay,
I
cool.
think there's a lot of teaching moments in here. And in general, uh, starting first with like general board layout, it's really hard to visualize like what this should be, how it should be laid out. There was no guidance on that. I mean, it's got a screen. I probably would have rotated the board 90 degrees, but they said 160 by 100, and I'm sure they meant hamburger style, not hot dog or whatever. So just kind of trying to infer some things, but
I think you might be reading too much into that.
if it were my product, I would care a lot about where the connectors were, where the
Hmm.
buttons were, where the screen was, and not so much everything else. But I don't think that's part. We're not designing a product for this. I don't think so.
Well, let's start with, I mean, we could spend an hour on anything. So let's start with your top priorities and work our way down.
Cool. Yeah. So this now that I have it all kind of in one spot helps visualize what we got. So there's like 4 voltage regulators for the 4 different voltages. Um, there's these little cutie, little tiny. You get an idea how small these are compared to a pin header, right? These are the motor driver chips. Um, out of here, there are a couple differential pairs, but trying to keep things together in the logical way. There's 6, I think, identical connectors, but they all have different stuff going on. Looks like it's meant to plug into some diagnostic equipment, obviously plug into, well, not obviously, but plug into 2 different motors and some other stuff. So yeah, let's go back to the schematic. And I think there's a lot of teaching moments in here. I'm certain of that. So I can say, not knowing better, what I chose to do was have, so there are 2, well, there's 4, 2, 3, 3 grounds. Let me go back to the PDF real quick. This page. So this didn't show up in that top level diagram. So what we have is 3.3 volts, 5 volts, 15 volts, and -15. And then there are 3 grounds. I think grounds is the right term. So there's chassis, there's this analog ground, and then there's also a digital ground. I'm guessing RTN stands for return. I'm just guessing.
Yes. So calling it ground is something everybody does, but nobody should. They're return paths. But there's so much. I really feel like we should probably start off with your impedance question, because it's going to fill in with everything here. So what is your, go ahead.
Let's look at what they wrote, and then we can try to understand it. So there's a lot of, let me find that.
Single ended 50 ohm, differentials 100.
So first of all, what does single ended mean? Does that just mean one trace alone?
Yes.
Is that right?
Yes.
Okay. And then differential, I assume, means 2 wires running next to each other. A differential pair like USB or anything that gets called out as a differential pair.
Yes.
So I do know about this nifty thing. There's a calculator built into KiCad.
Oh, that's adorable.
And if anybody wants to know where it is, it's right here. It's a picture of a calculator.
That is absolutely adorable.
It's even got little pictures of stuff.
Oh, that's too cute. I want that on a keychain.
So it seems to me like, based on my Googling, that impedance is not related to the length of a conductor. Can you explain, Correct. Is that true, and why? Why is that?
That is true. So what is your understanding? Because before you said you think you know what impedance is, but I want to challenge you on that a little bit.
Okay, I don't know what it is. I feel comfortable with the concept of resistance, and my basic concept of impedance is its resistance for AC versus direct current, or something of that nature.
That's all fair. So let's back up a little bit. Just because I have trouble remembering with everybody. You didn't have the physics background, right?
Nope. I have like a no background, so.
That's okay. But you don't know what like Lenz's law and Faraday's law and all that stuff are. That's someone
beyond hearing terms and like bumbling through Wikipedia. No.
Okay. Now I just wanted to make sure I wasn't like talking down to you or anything, because like if I explain things one way to somebody with a physics degree, I'm going to start getting some, negative reviews over there. So you are, I'm sure, familiar with electrostatics, right? Opposites attract, likes repel.
Yep.
And you're probably also familiar with a similar phenomenon with magnets, right? North and north, south, south, and all that.
Yep.
So those are 2 aspects of this thing that we call electromagnetism. They're intimately related, but they're 2 phenomena that are seemingly separate. And we can figure out how much energy that you can store in an electric field with this thing called permittivity. It's a fundamental constant of nature. And, if I have 2 electrically charged objects, they'll attract and or repel one another. And then if I put in an insulator in between them, I can actually use the fields of one to start messing with that insulator a little bit, and then that can impact the fields of the other. So I can actually store more energy in between two things if I put an insulator in them than if there's nothing there at all. I don't feel like I did the best job of explaining that, so let me take another run at it. Anytime that you have two differently charged objects, right, they will either attract or repel each other. And you can extract a certain amount of energy from that, or you can put a certain amount of energy into it. If you put an insulator in between them, that number goes up. The amount of energy that you can store or extract becomes higher.
Okay.
What would be another good example? Did you ever wind a piece of wire around a nail when you were a kid?
Yep, I'm familiar with that. I have, yeah, and I mean, I kind of get the concept of like a solenoid, right? So you pass current through a wire, it creates a magnetic field that pulls on the thingy in the middle of it.
Right. Did you ever wonder why you needed the piece of iron in the middle?
I know you do, but I don't understand exactly why.
Fair enough. So that is a similar phenomenon called permeability, the ability to store energy in a magnetic field. So for electrostatics, we have permittivity, right? You put an insulator in the middle and all of a sudden you can store more energy.
So you're describing a capacitor then.
That is a capacitor. Now, if we take an inductor and we put a piece of iron in the middle, we can store more magnetic energy.
Okay.
That's permeability. So two different physics concepts, permittivity for the electrostatic aspect, permeability for the magnetic aspect. And depending on what materials we put in close proximity to it, we can store more energy and extract more energy. Kind of cool or not kind of cool?
No, actually, the analogy with a capacitor makes sense to me. So
Yeah.
that's good.
So it's just the way that things work. Now, I'm building towards impedance, I promise you. But you take these two things, which way do I want to go with this? Sorry, I'm thinking as we go with this. Okay, now you put an insulator in there, you increase permittivity. You put a ferroelectric material in there, you increase permeability, right? One's helping to store or helping to show the relationship between electrical energy and in charge. The other one's helping hi Chester. The other one's helping to show the relationship between magnetic energy and current, the movement of charge. It turns out that those things are pretty closely related. Whenever you have a changing current, it creates a changing magnetic field. That changing magnetic field creates a potential difference. The potential difference can cause charges to move. All this stuff is incredibly related because even though we think of electricity and magnetism as two different things, they're really different aspects of the same thing. All right, now coming at it from another direction. When you create a disturbance in that field, that disturbance travels outwards at what we typically think of as the speed of light, right? 300 million meters per second. Were you on the call when I was able to show that animation of the wave?
I wasn't on, but I actually did watch it. So
okay, that was pretty cool, right?
it's nifty.
So sometimes you get changes in the field happening so fast, that they propagate away before the energy can return to the object. Well, as they propagate away, they do so in I'm going to call it a dance for lack of a better term, where as the electric field changes, the magnetic field changes, and then the electric field and the magnetic field. And they're tightly related to each other. The changing magnetic field creates the changing electric field, which then creates the changing magnetic field. And you're back to this whole permittivity and permeability thing all over again. Now, Where impedance comes into play is that it's the relationship between the permittivity and the permeability.
Okay, let me see if I can ask it in a different way that will maybe help you explain it a different way. So, a direct current through a wire makes a magnetic field, right? But nothing exciting is happening. It's just there. So, do we get to ignore impedance when it's a continuous current?
Yes.
Okay, so this only happens when we're changing it, like,
Yes.
and I'm guessing rapidly, like not 1 hertz, but like kilohertz or megahertz. Was there a threshold where it's like close enough to DC that we don't care, or
yes.
is it only when it's changing?
Sub kilohertz, it's close enough to DC, we don't really care.
Okay.
But man, there's nuance in that question too. So let me go back and review all the things I've said, because I'm trying to, by the way, build this pathway as I describe it to you. It's not easy for me to do. Changing magnetic field, permeability, changing electric field, permittivity. The energy that's able to be stored is reflected by the coefficient in whatever that constant is. Except electricity and magnetism aren't separate things. They're different aspects of the same thing. So whenever you have an alternating current, it creates changes in the magnetic field, and it stores energy in that magnetic field. And then if it changes back again, well, there's no time for that magnetic energy to go back into the wire. So it radiates off into space. And as it radiates off into space, the changes in the magnetic field create changes in the electric field, which then create changes in the magnetic field, which then create changes in the electric field.
Okay, so let me repeat that in a different way. If we have,
let me just finish that thought real quick. The relationship between that change between the magnetic and the electric and the electric and the magnetic is impedance.
Okay, so if I were sending a changing current through my conductor, I'm trying to it's trying to make a change to the magnetic field that surrounds it, and that isn't free, so it requires energy to make the change to the magnetic field. Is that reasonable?
Yes.
Okay.
But that's just the magnetic aspect.
Right.
The permeability.
Don't worry. Explain it how you think is best. Hopefully it'll help somebody.
No. I think
it helps
you're good.
Me too.
No, keep stopping me. So yeah, if you have a changing current, that's going to change the magnetic field, inductance. That's going to change the amount of energy that's stored around that conductor as it goes through. So let me get my example wire here. So here I've got my wire. As any current travels around here, energy is going to be stored circumferentially around the wire. Now, if you have a change, if suddenly more charges are going through here in a given unit of time, more energy will get stored around here. Also, at the same time, if I surround this with a ferromagnetic material, I can store even more energy into it. Anyhow, so energy is getting stored around the wire. Now, if I suddenly stop the current from moving, well, some of that energy will try to go back into the wire.
Okay. So somehow it makes sense to me when you're using, say, a relay and you switch it off, all the energy stored in the relay's coil will basically go backwards, or not backwards, but it will go back into the conductor, and you're going to need a diode to protect the circuit that's powering it, right? So, okay. So it's kind of, it's resistance to the change of current, not resistance to current itself.
It is exactly resistance to change in the magnetic field.
Okay, which is caused by the current. So Okay, so that's the relationship. So all of a sudden, that makes way more sense now.
Okay.
It's all a matter of saying it correctly. So that makes sense. I understand that. So when it's a single conductor, that seems fairly straightforward. How about in this case where there's two? Is the reason that we care to calculate this differently because the magnetic field that's generated by this one is having an impact on this one and vice versa?
There is always a second conductor.
Okay, yeah, that makes
No, no,
sense.
no, no, no. Remember what I said earlier? You said, why didn't they call it ground? They called it returned.
Right. Yep, that
So,
makes sense.
so whenever you have a wire and you have that changing magnetic field that, like we're going to drive this, where's my camera? We're going to drive this top wire. So I have a changing current going around this wire, right? That magnetic field isn't confined to that wire. It's going to spread into this one. So that energy, that radiating energy that we saw in that cool diagram that I showed you, that energy is going to be absorbed by the return current path.
Okay. Okay, that makes sense. I guess what I mean here is this one, if you can see
I took your
our
screen
first.
down to let Brian
Oh, okay. Yeah. So that's fine. You don't have to show it. But in the case of a pair of conductors,
in. Mm-hmm.
and there will also be, I would call it a ground. In the case of a differential pair,
Uh-huh.
is the return path still the ground? And then these
Yes.
two are just okay. So yeah, so there's this little deal here where it says odd and even, and I think that picture represents when they're both changing in the same direction versus they're changing opposite to each other.
Yes.
And so you
That's
get a
right.
different number for impedance depending on that. But
Yes.
so two unrelated like digital signals next to each other would be sometimes odd and sometimes even.
Yes.
But if it's a RS 485 or whatever, it would be they're both changing in the opposite direction at any given time, right?
Allegedly.
Allegedly. So we would think of that as odd.
Yes.
So what would ever be even?
So that's a great question. So, okay. You're asking really good questions, by the way. These are great questions. Now, remember how I said that the relationship, depending on what material you had around that would affect the permittivity and the permeability? And that permittivity and permeability, when taken together, give you a the square root. I always get it backwards, but they give you a something that is directly related to the speed of light, the speed of causality, the speed that those changes happen. So can you imagine then that as that electric, if we were just talking about the magnetic aspect for a moment, that as it reached this coil, something different would happen than when it was over on the rest of it?
I think I follow.
Is that, would you agree that, something different is happening if we're pretending, of course, this is a wire and this is a solenoid wrapping, right?
Right,
Would
sure,
you,
of course.
something else, it's going to be behaving much differently here than it is in the rest.
Right.
So the same thing happens when you run traces over fiberglass. When they're over epoxy versus when they're over the weave, they have different speeds. So a differential pair that might start off with these things exactly out of phase, exactly odd. It
Mm-hmm.
doesn't take much distance before them to have very different life experiences. And these things will go from odd to even to odd to eat, whatever. It really doesn't shift that much, but they do shift quite a bit. So that's why you always need to have the differential pair coupled to a return path, not to its neighbor. Because
Okay.
they're going to be traveling at different speeds. So the transitions are going to be happening in not necessarily where your mind might envision them happening. They could very well have the same polarity in certain aspects.
Okay. Yeah, because it seems like here, what I just can't think of an actual example of what would be designed this way. I would call it like a Skemerential pair, right?
We do design things that way, but I don't think we want to go down that route tonight.
Let's not do it.
It is something that happens unintentionally, and one of the things that's going to blow engineers' minds and make them leave nasty comments on YouTube is you could, if you wanted to, route that differential pair in opposite directions around the edge of a board. As long as they get back together and it takes them the same amount of time to get back there together, your signal's going to make it. I wouldn't do that for this competition. I'm just saying you could. All other things being equal. Okay. So then impedance is the relationship of that changing field energy, the magnetic to electric to magnetic to electric. And depending on what materials you're traveling through, you're going to see different permeability, different permittivity, therefore different impedance. So if we back up then to what is resistance, what is capacitance, what is inductance? Inductance is the ability to store energy in a magnetic field that encircles a wire. Capacitance is the ability to store energy in an electric field between two conductors of different potential difference. And resistance is the ability to cause mayhem in a wire by scattering electrons and charges in every different direction. And when you take those three things together, you get impedance.
Well, it makes sense that didn't make sense. So originally, yeah, it's like that level of calculus I never quite reached. That like I got the basics. So thank you for explaining that. Actually, very helpful.
Sure. And the rules are different. If I take somebody who's got a physics degree versus somebody who doesn't, and I start throwing physics terms in there, which I did, it's not really fair. It's just I have never been challenged to explain it in a different way. So
yeah, I've tried to avoid the pitfall of saying even if I don't understand, because it's easy to do, and then you end up moving on. You don't really learn anything. So
no,
always good to start from the bottom.
So let me check for understanding then. Now that I've had a chance to ramble on for quite some time, what do you understand impedance to be so far?
It's the resistance to changing the current in a wire rather than resistance to putting current through a wire. That's my super simple understanding.
Okay, we're not quite there yet, but
then.
We're at least further along than we were 40 minutes ago. So that's good. Now, as it applies to your competition, we typically route differential pairs next to each other so that if they do experience interference, they will both experience the same amount of interference, and any voltage offsets that they receive, they'll receive equally. So then we can subtract them out, negate them. When you see calculators like this, like KiCad has been so kind to give you, they're not actually all that useful because they don't take into account everything that a fabricator can take into account. Like if you go to Royal Circuits and you say, hey, I need a 50 ohm single-ended line, and on layer 2, 100 ohm differential pair, layers 4 coupled to layer 5, whatever. You go and you take and you here's the stuff. They will go and not only calculate what materials to go grab off of a shelf, right? They'll also be able to calculate how much squeeze out there's going to be. Because when you laminate these B-stage pre-pegs together, they squeeze some epoxy out the side. So they're not going to be the same height that it says in the specification sheet. But, you know, since they've been doing it for the last zillion years, they know exactly how much is going to come out. So even if you go and that calculator says, you know, I have a 3 mil layer height and, you know, and I can't see because it's too small on that screen.
Oh,
But let's say it's
sorry.
14 points. No, it's fine. It doesn't matter. Let's say it's 14.7 mil. It gives you 14.7 mil trace, you know, 13 mil space, whatever. I don't care. Well, by the time you take those numbers over to Royal, they're going to have to change them for you. They're going to say, okay, you want this to be 3 mil. We've been doing this a while. It's going to be 2.7, which then means your trace and space numbers are going to be different anyway.
Right.
So,
and does that mainly apply to if you're coupling something from one layer to another? Because I would imagine if they're both on the same layer, then just the width and overall, like that seems like it would be less variable or less prone to that type of
okay, so
thing,
there are,
right?
yes, there are ways to minimize it. Like if you design it on a core, which has been laminated by the material maker, you know, weeks ago, that you won't have squeeze out there. And you can do edge coupled, you can do broadside coupled. There's a whole lot of nuance in it, Elliott. You don't need to be too worried about for this competition. Plug some numbers in, get some numbers, and use them. Right? These guys are running 140 volts through a 12 volt part. They don't care.
That's my plan.
But yeah, realistically, if you were doing this in a design environment, I would tell you to contact the fabricator and say, hey, I know I'm going to need 2 differential pairs. Can you tell me what my numbers need to be? And let them do all the math for you.
Got it. Brian, I don't know if you caught it. This is the part. It's the size of like 2 grains of rice.
I saw, yeah. That whole section of the board would melt with that much electricity on it. So
I'm gonna draw a little explosion in the silk screen around it. See if they like jokes or not. I'm not sure.
They will. Okay, so you still have to route your differential pair. The typical rules for that: you don't want to break your ground plane or your return path. It needs to be continuous. You don't typically want that pair to change layers, because if you do the calculations on layer, say 2, and then you move to layer 1, well, on layer 2, I've got copper above and below, and you calculate what your magnetic field is going to look, an electromagnetic field is going to look like around that. Well, when you go to layer 1, now there's material underneath, but there's air on top. So now the field changes. So typically what you'll do once you figure out what layers you're going to route those on is just leave them on that layer and let those have routing priority.
Gotcha. So I'm not sure I did what was right, but I did what felt neat. And so I have this situation where I have these 2 pins for the pair, and I have a second pair here, and they need to end up on these 2 pins of this chip. And unfortunately, it doesn't seem to matter which way you rotate things. They always would cross unless you come in from this direction. But this was kind of what I came up with here. So it's this net. Don't worry about that stuff. And then this one here.
Okay.
So
why did you put that meander in?
I was trying actually an experiment with the little gizmo here that can make traces the same length. Or
okay.
you can adjust the length. I found out that you can read the length of your conductor here. So they're within 0.2 of a millimeter, but I don't think that makes a big difference, especially over this distance. Is that a correct assumption?
That is likely a correct assumption, yeah. These are lumped elements at that distance. It really, what you want to design to is not length. You want to design to time, but very few EDA softwares actually have that capability to time match. So we length match as a close approximation. But over this short distance, I can't imagine it mattering. But it looks cool. It shows that you care.
Right? The second differential pair is on the bottom layer of the board, and it does a very similar thing, but I have this problem, and I don't think I solved it very well, is I'm actually coming on the bottom of the board up through Avia and then into the pins
Cool.
here. And
That's
this one has the same rotational challenge.
That's a perfectly fine way of solving it, but you want to usually add some ground return vias.
Okay, how would I do that?
So you would create some static vias on, it looks like you've got room for certainly the one on top, perhaps at least one, if not two on bottom. But you would create static vias and you would connect them to the ground.
So just near these is what you're saying?
No, right next to them.
Right, but not connected to them.
No, you would put those next to the vias.
Oh, here.
Yes.
I see what you're saying. Okay.
There.
Right. So as many as you can possibly have. What's
for what you're doing, just put one.
Okay.
Who cares?
I'll remember that.
But remember how I said, you've got this electromagnetic field that surrounds it, and you need a return path to capture that energy.
Mm-hmm.
Well, a via is a vertical interconnect. You're still going to have energy coupling around that via. So if you put a ground return, it'll then translate up into that space and it'll be absorbed by that other, by the return via, and it won't radiate off into space.
Gotcha. So I think this, let's see. Sorry for all the colors if anybody has like an aversion to that. So this is using the, what net is it? Yeah, pink one as its return path. And so because there's the clearance here, and I think what you're saying is because the via is perpendicular to this pink plane, that it's not going to couple into it. It's only going to be coupled for the parts that are parallel. Okay.
And you'd want one for each via.
Makes sense. Okay. I'm learning lots of tricks here. If you hate doing this, and every time you draw a via, you have to select the net for it, if you have a pad or a trace anywhere nearby, so here's, well, let's just take this 5-volt one. If you drop a via on something, it inherits the net, and then you can just pick up and move it. So cool. It's handy because drawing them over and over is really annoying.
My only question is that your analog return?
Yeah.
Should be your digital.
Well, let's see. Yeah, I think you're right, but let's check out whatever U8 is. Because this is only connected. So this is what I drew. I've got analog, analog, analog. And what the heck page was that? What is this page? That doesn't look familiar. INA 33 something. Okay, let me figure out what page we're on.
So analogs. God, okay, I'd have to look at this.
Yeah, let's get their document here. That was not this page, not this one. We're gonna find it eventually. Everything's off by one.
No, it's fine, man.
Stop. Tell me to stop when you see something that looks like that picture. So that's yeah, I think.
No, go up. There. I mean, they're calling that a differential.
Yeah, so this is a different
Okay.
component. This is U9. A, B, C, D.
Well, the draft site document should all be auto hyperlinked. You should be able to click all around.
Oh, yeah, good point. So here, U8. We're at the right place. So yeah, I think I got that. We got analog, analog, analog.
It is. That's their analog. Interesting. So they're
Well, good news is that I didn't mess that up.
no, you didn't, but I just have so many questions about this sample schematic that they gave you. I would have to sit and study it some, which I don't have time to do, but
No, yeah.
yeah, I don't know, man. Okay, it's cool. Just roll with it. Let's not worry
That's what
about
we're
it.
doing.
Yep.
I'm not totally sure on this like 50 volt 1 amp scenario here. Maybe that's only meant for isolation, but this doesn't seem like a component you'd be putting an amp through. Maybe it is.
No, you wouldn't be putting any current through it. It could maybe drive a little, but it wouldn't be picking up much anything off that differential pair, and it's an op amp. It doesn't matter. Just roll with it. Just
Yeah. Yeah, it's a lot. There's a lot of stuff crammed here. And I think there's actually one note in there that says density level B. So I need to start counting things and see how close they are together. I realize now that I'm done. I have a lot of room left over, but spent a lot of time just taking, for example, I took the 140 volt motor controller, and my goal was basically I'm going to put that as close as I possibly can to the 140 volt input and make that whole situation as small as I can so it doesn't get in my way.
that's good.
Um, so this is somewhat duplicated. Another thing I find very frustrating with KiCad, and if anybody knows a better way, is making things symmetrical or mirrors of each other. I think that's probably just like vanity, but it really bothers me if like these components aren't aligned with these ones. I know you can use the grid, but what I found is like depending on the footprint you use, unless you make all of your own, they don't all have the same origins. They don't snap to the same places. So like lining up the edge of two components is quite difficult. Now there is a menu item here where you can align things to different parts, but you have to use that dialog every time. You can't move this around and have it snap to being aligned with anything near it, like a lot of other CAD programs. So
Yeah.
quite irritating. I won't tell you how much time it took to make this look like this. it was too much. But yeah.
Interesting. All
I
right.
feel your pain, man. I feel your pain.
Yeah, there's probably a lot of other questions, a lot of other good stuff in here to peek at. I've never laid out anything quite like an FPGA, and I have a feeling there's like a recommended, well, there's a good workflow where you start with X and then do Y. I just kind of started with let's hook it all together. And then also, I'd love to understand. So I have, you see on some boards where they have squiggles, which I have a feeling this flash memory is pretty slow and tolerant of timing. But when does it matter to have equal length traces, and when doesn't it matter?
Oh, Brian, did we lose you?
There, no, I'm here. There was
Okay.
it was actually a good, one of the things on the Adafruit YouTube channel is a thing called Colin's Lab Notes. He does a little 1 minute segment on each day on something. And he talked about those little squiggly lines. And it's just with, if you've got signals that are fast enough, they've got to arrive at the right time at the other end.
Right. I think they
And
call that skew, right?
yeah,
When they don't arrive at the
right.
times they
Yeah.
left.
That's why like Mark was saying, since we can't easily calculate for time, we use length as a as an approximation. So it's I think you would know if you had a timing situation. I would think it would matter with really fast, well, like our data buses that depend on a clock and an enable. That the clock's always running, but the enable goes up, and that's when the data starts flowing. If the clock and the enable are in the wrong, not synced, you're going to get garbage. So
Brian's right. That is when it matters. If you've got, say, an edge triggered or an edge sampled thing, you do sometimes have to worry about that. However, the number of boards that I've seen that have done those little meanders that have needed them is so much smaller than the number of boards that use them that don't need them or actually need them. I said that backwards. A lot of time people are wasting their time putting those in.
Makes sense.
Is
Yeah.
the right way to put it.
I do wish that I could have chosen the pins they used on the FPGA. Would have made this a little easier in some cases. But yeah, I end up with some of the data lines doing this long whoop-de-woo. Address lines are real short. But because it's a square, I think this is a PLCC, it would be awesome if it was rectangular or some other situation where it was really straightforward to make the connections.
Can you put it on the other side of the board?
They didn't say I couldn't.
I mean, I wouldn't. I would leave it the way you have it, but I'm just saying if it's making you all itchy.
Oh, no. I was actually pleased. So it probably would have been easier to use all 4 layers, but I actually am only using them for the analog and digital return. So this is all basically a 2-layer deal. And most of the traces have 1 or 0 VS in them. There's a couple with 2, like this guy, but that's when I was getting to the end and it was like, I'm just connecting the dots now.
Well, Elliott, man, you were doing, for a guy who's never done this before, man, you're doing an amazing job.
Well, thanks. Yeah.
Yeah.
I got to say the software is probably the more difficult part than connecting things together. It's, yeah.
You certainly
at
use it.
least your things are connecting in the right order. I've had several things where I've had multiple crossing traces because pins were in the wrong order.
If you look at this situation over here,
most of it I fixed because I can define.
Good job.
But
yeah, this was
familiar with that
so
pattern.
I think these are resistor arrays, not networks.
Zoom in on that real quick.
This situation here.
No, that part I'm cool with. I was wondering what was happening up here.
So these are, I think these are arrays. So each one is a resistor. They don't have a common pin, but they're in the same shape as what I used to think of as a resistor or a network. But what would have made this better is if they had changed the pin order on the FPGA. So basically, these are straight in the same order on the chip as they are on the LCD. And then these are all mirrored. So basically, you stretch out the rat lines and they all intersect. None can go straight.
I don't think we often get to pick the pin ordering on the processor or whatever because it's just.
Well, you do if it's your project and you're just
more often
GPIOs, right?
More often than you think. Okay, so here's what I'm thinking, Elliott. What if? Okay, so a couple things. So Brian, there is this thing called pin swapping, right? You do sometimes get to decide. FPGAs are very very malleable pieces of hardware that you do often get to choose what pins connect to what, and you can do that to simplify routing. It's a little bit of back and forth. Do you need to come back to the top side of the board? You've got plated through holes for pins, looks like 8 through
Right.
15,
So
14.
I need to make these connections to the FPGA as a surface mount resistor. And I can't, even if I stick this right up next to it, they still all intersect.
On that side of the board?
Well, let's just do this. Let's see what happens.
No, don't move that. What did
I've
you
got
do?
I've got
No!
an undo button.
Ah!
Save.
Oh, whoops, I can't select the proper item. Yeah. So this guy, if we rotate it, you can see, I feel like this is really nice, right?
Mhm.
And if you bring over these, they are all close together, but they all intersect, unless I were to do some weird thing, like put it over here, right? But when they're,
Put it on the other side of the board real quick.
that works.
So just that gets you down to 1 via.
Well, I still need 4.
Well,
Yeah,
but
but
I
he's
don't
saying
need
1
8.
per line, I mean.
Yeah.
Yeah. I don't need 2 per line. So then, what's your opinion on having surface mount components on both sides of a board? You got to glue them on the bottom, right?
If you can avoid it, avoid it. But
Or maybe
this
a different way to
project-
ask it: what number of vias is worth putting things on the back?
it is totally worth for a project that you have to pay for. 2, 3, 4, 5 vias, go for it. I don't care. For this project, where they're going to be judging things based on if they look nice, I don't know. And even if I do know, I don't think I would be allowed to tell you if they're going to be adjusting assembly cost. I don't know. But
I'll have to read the directions.
I'm worried about the via copper to copper clearance on the vias that you have up there in that arrangement, in that linear arrangement.
Sure. Yeah, I think we're going to do better on that next time. They're not even in a straight line.
Okay. No, I mean, down at the bottom, no problems. It's that line up at the top where I'm a little... I mean, yeah, you will have
these
to
guys.
move...
Yeah. These can be, we can spread all of that out.
Okay.
I actually don't even know if these are the right size vias. I just started slapping them on there.
Yeah. No, I think down at the bottom you can move things around, but in that same basic pattern, and you'll get things to fit. It was just up in this corner I was a little worried about.
Yeah. I'll definitely adjust that. But yeah, this is it had to twist. There's a twist in the wires, which is very unfortunate.
Yeah.
So that's where, since it's an FPGA, it's like, dang, we could have just selected the other.
So you've done
choices.
all of this on one single-sided,
Single-sided
2-layer design.
2-layer design with the returns on the inner layers. Yeah. So that was something I saw Jesse mentioned that he tried and liked it. I think on Monday he said that. I was like, oh, I'll try that.
Yeah.
What do I got to lose?
I like that's how both of us did our boards, because, well, I mean, I was in a rush, let me tell you, to get my board out. And that's the fastest way to do it. I didn't have to route it.
It did feel very easy to only have to think. Well, not easy, relatively easy to only think on 2 layers, because having 4 and visualizing how things are going to go feels a bit more intimidating.
Yeah. Now I've got another question for you. So you've got a separate digital ground and a separate analog ground.
Mm-hmm.
How are your signals going to know which ground to go on?
Well, I would say based on what they're connected to, but that's probably not the simple answer you're looking for.
They're going to couple to the closest bit of copper that's around. A digital signal won't go through the analog ground to get, or the analog return to get to the digital return. An analog signal won't go through the digital return to get to the analog return. They're going to go through the closest bit of copper they can find. So stitch those things together with vias. Stitch your digital to your analog ground. Make it one big ground.
Okay, let me double check something.
Unless they specifically told you you can't.
Well, I'm not sure what they told me, but let's see. This is, I don't know, this PDF viewer is the opposite of normal programs when you pick up something. This is what I see is a resistor between these two.
Star point 49.9
Ohms, I guess, yeah.
1 watt.
So this tells me it would probably be incorrect to stitch it all together.
Well, that tells me that the person who made that schematic thinks it's incorrect to stitch it all together.
Right, okay.
We can let's get Jesse's opinion on that. I mean, if obviously here they want you to keep them separate, but man, I would just stitch those things together in a heartbeat.
So if you were considering stitching them together, would it be just as straightforward to have one? Like, is it having two, if they're not separate, is the only benefit that you have them very close to the layers? So if you stitch two inner layers together like that, what's the difference between doing that and just using one inner layer as your return for both digital and analog?
Well, there are height differences. So
all the traces on the bottom would be further away from that middle layer that's close to the top, basically.
Yes.
Okay.
You want your return generally to be as close as possible.
Okay, makes sense.
But given that scenario then where they do want to keep things separate, and given that you might be willing to rip everything up and put it back down again just because you are learning, you might consider putting your analog components on one side of the board, your digital components on the other, and then having those internal layers be the returns if you're going to do it this way.
Interesting.
It'll give you a ton more space that you obviously don't need. You've got room to spare as it is.
Yeah. Yep. That's like what I said. This is the first try, and I was just going to see what fit. But I expect to take it apart at least once because I want it to be fancy looking. And I'm sure there's some clever ways, things I could have put much closer together.
You've done a heck of a job.
Well, thanks. Yeah. Just learning, but I will say it's a challenge.
It always is. Let's see. Paul is commenting. What does Paul say?
Other EDA tools have a way to replicate the layout of a hierarchical page. So actually, when you first create the schematic, it does kind of do it. I don't know if that's what you're talking about, but if I were to, I don't want to delete this. Let me save a copy of it somewhere. All right, I have a copy. If I were to, let's see.
I will say this though, Elliott, man, I wish I had picked this stuff up as quickly as you seem to have, man. That speaks volumes for your capability to learn and your desire to avoid sleep to get things done.
Well, thanks. Yeah. The trick is you skip right past the fundamentals and you go straight for just diving in.
And you know something?
Some of us can do that, some can't. I can do it okay, but it's.
You know something? You don't need to know the things that are rattling around in my little physics head to be a successful PCB designer. And oftentimes I get stuck in analysis paralysis because of it.
I believe it.
by all means, for what I'm seeing so far, don't go the route I did, man. Go the route you're going.
Well, good news is it's, I won't say too late, but that's a huge investment now. So, so I'm not sure if this is what you meant in that comment, but it does group everything by sheet when you use a hierarchical sheet. So if you draw in that way in the schematic, this is everything that's on one page. This is everything that's on another. So it does actually do you a favor. I think, Mark, when you were sorting them out in dip trace, you were just kind of picking and choosing by the
Yeah, it wasn't.
sort of underscore one situation.
Yeah.
You can see here we got all the ones and then all the twos. So
Oh, yeah. See,
were,
that's what I was doing manually.
yeah. So at least we got that. And
I think I might have been a little late to find that comment. I think that was back when you were complaining about its capability of mirroring things.
That, yes, I'd love to know more.
Yeah, but yeah, what you just did looked like something dip trace should do.
Yeah, this is like it's a no-brainer. So no complaints about that.
So cool. Brian, anything we can do for you this evening, sir?
No, just hanging around.
I appreciate you hanging around.
Well, thanks for letting me suck up all the attention.
That's what office hours is, man.
I'm learning.
Okay, I see Paul posted
with your questions, and we try to answer them. That's good. Hey, before I let everybody go, I've got a question for you. Do you notice anything different tonight?
Did you get a haircut?
No.
Dang it, that's always the answer to that question.
I put up some new lights right before we started.
Yeah, now that you mention it, I think that's an improvement.
It is. I mean, I'm not done yet. I just got 2 going, but like they dim and stuff.
Yeah. Well, lighting is one of those things lighting is one of those things that if we don't notice, it's a good thing.
Yeah. Well, I mean,
because you won't notice when something improves like that. It's like, oh yeah, he's looking natural. It's fine.
Well, I need to keep working on it. But one of the reasons I never bothered doing it, because most of the time I'm making these videos by myself and nobody watches them. So who cares? It's no point in investing. But now I'm starting to get a following. I have, 2 people. I can count them on one hand still, but I have 2 people that come regularly. So
we just like attention.
Hey, no, that's great, man. That's what office hours is supposed to be, though. You guys come in with your questions. I try to answer them. And man, it was a little bit of a struggle at the beginning, but
don't worry, you're answering the hell out of my questions, so it's very good. And thank you.
Good. So, all right, gentlemen. Well, unless we need another office hour this week, I think our next one will be probably the next time we get together will be sometime Sunday, for the next week's announcement, which is schematic capture. That's exciting. And I might even release that material early just so people can get started on it heading into. So we're just that much sooner heading into the Thanksgiving holiday for board layout.
Yep. I don't see any harm in that because symbols are less exciting.
Well, I'm also trying to remember, I've already lost probably, I'd say 12 people had sent me emails. It's like, Mark, love the course. Wish I could keep up. Life's getting in the way. I don't have time for the course. What would be brilliant, I think, if we're able to continue doing this type of thing in the future, is have cohorts that go at different speeds.
Yeah, or even have checkpoints the whole way long, where every week when it's completed, like here's a project file in your software with all the footprints in it. Here's one with the footprints linked to the symbols, and like here's one with the schematic completed, which you will do, I think, along the way. But even then, it would possibly help even to have those at the beginning of a week, so you have an example of a good example of what you're trying to do. Sometimes that's nice to like pick apart, and I know the libraries are there in the software, but
Yeah.
I don't know. Don't want to give the answer before we figure it out, but that's sometimes the best way to learn is take something apart, see how it is.
Well, also remember too, man, we're just staying ahead of you guys. So writing is not fast by any means. So, you know, when I offer you these things at the end of the week instead of at the beginning, I don't have them yet. But we will in the future. Right? We should be able to repeat this project. We can't repeat the last project. It was too difficult. And we can't get the parts. We can work around this project and work around part shortages. So moving forward, the course could look different than it does now. We just have to keep that stuff in mind. So
Right on.
Yeah. Hey man, keep up the good work. I'm going to be blown away if you win this thing, only simply because the other contestants fall out due to attrition.
If 19 other people don't turn theirs in, I'm totally going to win.
You're doing really well, Elliott. But with as much work as I'm seeing you put into this, who's got the time?
Well, I have the benefit of getting that like work from home situation. So, you know, kind of live in front of the computer.
I was looking at that schematic. I don't even have time to capture that schematic.
It took a good part of the weekend, but it was raining, so good excuse. Yeah, the schematic was pretty brutal because, I don't know, I made a lot of typos, and it was tough to pay enough attention and read through those list of pins to make sure I got all the symbols in the right order.
Yeah,
that was. I'm sure there's a good way. I did it the hard way.
I hate schematics that are connected that way because you never know where all you need to look.
You can't visualize it either. You can't visualize like this line's in the wrong place. No, it's like this word is slightly different than that one. And when you have underscore 1, 2, 3, 4, it starts getting double underscores like 1, 1, 1, 2, 2, 1.
Yeah, I don't like. I know there's some designers that put those out there, and it's great if you're the designer and you're working on that project again in 2 days. But if you have to pass that over the wall to somebody else, or you're coming back to that project 10 years later, forget it.
Yep.
Forget it. So, all right, gentlemen. Well, thank you so much. Brian, we promise to let you talk next time.
Yeah. If I wanted to, I could have.
Just yell.
You let me in anyway. But
yeah, we appreciate the company. So
I'm going back to solder. I'm going back to learning how to solder. So,
all right.
Show us a picture when you're done. I'm curious to see how it's coming along.
Oh, there's one over in Showcase of my first couple.
Oh, we saw the first ones. I want to see your last couple now.
Oh, well.
Once you get to the end of the board.
I probably won't be able to even get a picture of those. Those are the tiny ones. I'm starting with the 1206s. The 402s are going to absolutely destroy me. I think I may not even do them. I'd like to. I look at how small those pads are with my current magnification.
If no one can tell if it's even on there in the first place, then does it matter if you even soldered it?
I'm sure there's some signal someplace that cares. But one thing I'm trying, Mark, you've probably seen on Amazon the cheap microscopes. They're like cylindrical things that are like $25 or something. Yeah, stuff very similar to that. Yes, I'm going to build a stand and play with it, and I don't have 150 to 200 for the cheapest of the built with the built-in displays, but
yeah. The issue that I have, maybe with the stand and you get rid of that little acrylic connector, but there's no working distance. You have to be pretty much on top of whatever it is that you're going to work on, and you're going to hit it with your iron. And I would much well, I don't want to say much. I mean, it depends on your eyesight, your visual needs and capabilities. But I would really almost recommend, instead of going digital at all, getting an one of those old ring light magnifier things that they have for sewing, for cross stitch, people that do cross stitch. See, I don't
You
even,
mean-
I've
you
never
mean-
liked those. Yeah, that one like you have in your hand. Does that have a magnifier in it?
Yeah, it's got a magnifier. It's I can barely see with these. Well, even the 600 series or the 603s will be fine. The 402s are just.
I can't
I
do
looked
it.
at them and I said, "Yeah, I can see that there's something there."
Yeah, no, I can't do it anymore, Brian. I can't.
Small. I can't even think about it. But no, I'm gonna see how I can do with these, and the fact that just the fact that the nice ones with a stand and display are so much more expensive is just puts it out of reach at this point.
Have
I need
anyone
other
tried-
things for a lot more.
They ever tried using like a DSLR with just a lens, a zoom lens, and stick it far away and really get in close?
That's what I have on essentially on camera 1, 2, 3, 4, camera 4. So this is a 50 millimeter telecentric lens that is seriously 2 feet above my workbench.
It doesn't give you much.
But this is the 50 millimeter lens.
But tons of space underneath.
Yeah, but I've got so much room for activities.
Yeah.
But really though, I mean, there is nothing I can put under here that I will ever hit that lens. So I like that. But that's the 50 millimeter. My camera that we're looking at right now that you're watching me on, guess who this lens is by? Arducam.
Nice.
I'm serious. It's an Arducam lens. It's all manual. You just futz with it. I wonder if there is I know you don't want to go out and spend $100, and I don't blame you, but I wonder if there isn't a microscope lens element that you can get off eBay and put on just an old security camera and get reasonable performance. That's what I have on this one. I don't have it hooked up because I don't have lighting ready to go for it. But this one is a infinity focus lens. But I'm just saying, if you do get a stand, it will help things, but you don't have the granularity of control that you get on a normal microscope with these. There's only 2 zoom levels. They say it's like 20 to 200. No, it's like 20 or 200. So I don't know. I would look around a little more before you go out buying. So
Yeah, I just trying to figure out something. Like like I commented earlier in the forum or in Discord, I'm trying to figure out what I can do with how little. I'll get the things I have to, but my pencil comes tomorrow.
Yeah.
For instance, but there's a lot of stuff I'd like to get, but until something changes, I don't have. I
don't have
just getting my parts ordered.
Yeah. I hear you, man. Well, let's follow up in Discord before you go down that $25 route. See what we can find.
All right.
All right, guys. Have a great evening. We'll see you next time.
Talk to you later.
Yes.
Bye.